Hello everyone. For today's video lecture, we're going to be talking about impulse and momentum in a rigid body system. So as we've seen before, when we move from a particle system to a rigid body system, we'll need to not only deal with forces, positions, velocities, accelerations, but also their rotational counterparts in moments, orientations, angular velocities, and angular accelerations. And the impulse momentum theorem is no exception. So we're going to need to consider the angular version of impulse as well as the angular version of momentum when we move into this theorem for rigid bodies. And before we do work with the impulse momentum theorem, we need to have a firm understanding of what angular impulse is as well as what is angular momentum in a body. So that's what these slides here are going to cover. So as a review for linear impulse, which is still going to be relevant for rigid bodies, the linear impulse of a constant magnitude force will be equal to the magnitude of the force times the duration of time. So this is kind of the simplest version of impulse. If we have a force and it is exerted for some period of time, force times time is the magnitude, direction of the force is the direction of the impulse. If we have a constant magnitude force, the linear impulse of any force is simply going to be the integral of the force function over that set period of time. So the integral of f of t dt, or if we have, imagine some force function over time, the area under that force function curve is going to be my impulse. These are both vector quantities, and again, the direction of the force is going to be equal to the direction of the impulse itself. Here in this course, we're only going to deal with constant direction forces. We're not going to deal with impulses from forces that change direction over time. All right, so the impulse of a moment. Let's modify this to deal with torques or moments. So the angular impulse of a constant magnitude moment will simply be equal to the magnitude of the moment times the duration of time. So K, which is the variable, capital K, which is the variable we use for the angular impulse, is going to be the moment times the time. And so when we have a non-constant magnitude, the angular impulse of any moment is equal to the integral of the moment function over the set period of time. So if we got some function for m of t, we integrate or find the area under the curve for that function, and the area under the curve is the magnitude of our angular impulse. Again, these are vector quantities. The direction of the moment vector is going to be the direction of the impulse vector in this case. So rigid bodies, we've got linear impulses, which before we just called impulses, and angular impulses, which is the impulse due to a moment. All right, so next up is momentum. So as a quick review, the linear momentum, which before we just called momentum, will be, the simplest form is the mass of the body times the velocity of that body. So m times v, and unlike an impulse which occurs over time, the momentum is instantaneous. So we take some moment in time, whatever the velocity is at that instant, times the mass, that is our momentum at that point. So we're particularly interested, usually we've got some initial momentum, some final momentum, and then the impulse is what changes the momentum in the middle of this. So momentum also has a direction. So the direction of the momentum will be the instantaneous direction of the velocity. So whatever the direction of v is, the direction of the momentum is the same piece, or is the same thing. All right, moving into the new piece, so angular momentum. So the angular momentum of a body at any given instant will generally be the mass moment of inertia of the body times the angular velocity of the body. So I times omega. And this makes sense. So I is the kind of rotational counterpart to mass. It is an object's resistance to angular accelerations. And then angular velocity, of course, is the angular counterpart to velocity. So I times omega would be our angular momentum. So just as with linear momentum, angular momentum has direction as well. Generally, the direction of the angular momentum vector will simply be the direction of the angular velocity vector. So whatever the velocity direction is, angular velocity direction is, that's the same direction we attribute to the momentum as well. All right, so complicating matters with angular momentum, though, is the fact that the angular momentum will depend upon the point we're taking it about. So unlike linear momentum, which is a single value, kind of there's only one linear momentum you can calculate in an instant in time, the angular momentum has a lot of possible magnitudes depending on the point of interest we are taking it about. And we might have different reasons to choose different points. We'll get more into that later, but there's lots of different points that we might take the angular momentum about. So we can technically take the angular momentum about any point, though we're usually going to take the angular momentum about one of 4 points. So the first one is the center of mass of the body. So our point G is going to be probably the simplest calculation. Next up, we have a fixed axis of rotation. So imagine a force pushing open something like a door, rather than the center of mass. In that case, we might want to take the momentum about the fixed axis, that in the case of door would be kind of the hinges on the door that the whole body is going to rotate about. We can also take it about the instantaneous center of zero velocity. So the instant center is kind of a temporary fixed axis. This is going to work much the same way as fixed axis rotation would work. And then finally, we have the point of impact in a collision. So this is not going to be not necessarily going to be a fixed axis of rotation. It's not going to necessarily be the center of mass, but at the point of impact in a collision, usually angular momentum is going to be conserved. So if that's the case, that's going to be a reason we take the angular momentum about that point for some given body. So let's go through each of these cases and talk a little bit more about that. So first one is the center of mass. So finding the angular momentum about the center of mass is probably the simplest. So the magnitude of the angular momentum will simply be the mass moment of inertia about the center of mass times the angular velocity of the body. So IG times omega. So IG is our mass moment of inertia. Again, you're going to go to the tables, look up that mass moment of inertia, and those values in the tables are about the center of mass. So figure out I multiplied by omega, you get your mass moment of inertia, or so you get your angular momentum about point G. And again, direction of angular momentum vector will be the direction of the angular velocity vector here. All right, so next up, I'm lumping these two things together. So the angular momentum about a fixed axis or about the instant center. So to find the angular momentum of a body rotating about a permanently fixed axis, something like the hinges on a door, or about an instant center, which is kind of just a temporary fixed axis, we need to adjust the point we're taking the mass moment of inertia about. So that's really the only adjustment we need to make. So IO is going to be the mass moment of inertia about that fixed axis times omega. Or in the case of an instant center, we usually use IC, so as the mass moment of inertia about our instant center times omega. So for this, we're simply going to use the parallel axis theorem for this adjustment. So again, IO or IC, IIC is going to be the mass moment of inertia about the center of gravity, plus my adjustment factor of plus mr squared. M is the mass of your body, r is the distance from the center of gravity of the object to either the fixed axis or the instant center, depending on what one you're aiming for. So we just have to adjust our mass moment of inertia, and then we find angular momentum based on the adjusted I value. Finally, we have angular momentum about any other point. So if we want to take the angular momentum about any other point, and again, usually this is going to be the impact and collision. That's the only real point we need other than the previously listed ones. We're going to include both rotational terms and translational terms in our angular momentum. So the momentum due to rotation is simply going to be the momentum about the center of mass, so IG times omega. So that term should seem familiar from earlier. But there's also the fact that the angular momentum will kind of take on a piece due to the translation of the body, because we are not taking it about the center of mass of our object. So this new term is going to be r g with respect to p cross product with mass times vg. So there's the linear momentum. This piece over here is linear momentum of the object itself. So r times linear momentum, or crossed with linear momentum. So putting this all together, we'd get the following. So IG times omega plus RG with respect to P crossed with the linear momentum of the body itself. So let's look a little more in detail about what all of these terms are in our situation. So say we've got some generic body and it's floating through space. There are 2 points of interest. So we've got the center of mass of that body and then point P, which are taking the moment of inertia about. So most likely this point P is the point of impact in some sort of collision. All right, so first term in this, so IG is the mass moment of inertia of the body about its center of mass. So whatever your body is, look up your I term about that center of mass, and that's the first term. So we've seen that before. Same thing with the second one. So this is the angular velocity of the body. So whatever rate at which this body is rotating, it is a vector. So in this case, it's counterclockwise, so that's positive z direction, kind of coming out of the page. Clockwise would be negative z direction, kind of going into the page. So that first term, we multiply those two together, and then we add on this adjustment factor due to translation. So we have RG with respect to P, and so what that is, it is the displacement vector going from the point of interest, P, to the center of mass of the body. So whatever point we're taking the momentum about, go from there to G. So figure out what that vector is, and it's going to be that vector crossed with the mass of the body times the velocity vector of the body at the center of mass. So figure out what the velocity of this body is, Vg, and you're going to multiply that by mass first, which is a scalar multiplication there, and then just do R cross momentum for the final piece. So there's a lot of stuff going on in this case. It makes it way more complicated than any of our other circumstances. But like we said, this point P, if we have that at the point of impact in a collision, it is going to be a conservation of momentum in that case. And so that's a very useful circumstance. So sometimes we will have to use this in rigid body collisions. All right, so that's all we've got for today's video lecture. Thank you for watching, and I hope to see you again.